This is the very first class in module 4 on the basics of instrumentation. Essentially in module 4 we are going to discuss about the issues of instrumentation, measurements, data recording, data storage, data transfer and so on. Because as you know, in condition based maintenance, the use of transducers is very important to know the conditions of the machines. Now, we had discussed that there are certain parameters which we use in condition based maintenance, like as in vibration, temperature, noise, electrical current. So, you must have studied in instrumentation, because this instrumentation itself is about a 40-hour lecture in any undergraduate program in mechanical or electrical engineering. But today in this class, in about an hour's time, we are going to overview the basics of instrumentation, and how in particular you will see in the subsequent classes. We will discuss about some of the transducers which are used in condition based maintenance to be put on the machines, so that we can capture the mechanical parameters of the machine, that could be vibration, noise, temperature, etc. And then of course, very important is we have to be very careful that we do not induce or do an bring in an extra noise or error into our measurement, because the algorithms of condition based maintenance depend on the data which has been collected by us or by the transducers and provided to the analyst. So, if we create noise or bring in artificial errors into the measurement system, we will not be doing a good job. So, other than knowing the instrumentation, the equipment and required to do the signal, acquire the signal from the machines, we have to be also careful about how, by doing a proper instrumentation, we can minimize error, how we can do the instrument calibration, so that we get the exact replication of the phenomena which is happening in the machine. Imagine you go to a doctor and he has a blood pressure meter which is which has not been calibrated. Okay, you can imagine the consequences. Similarly, when we want to capture certain parameters from a machine, we would obviously not like to do a wrong measurement. So, with this preamble, I would like to start this 16th lecture on basics of instrumentation. So, let us see what are the important elements of instrumentation. One, of course, is the sensing element or the transducer. Essentially, sometimes we have been loosely, sometimes people say that whether it is a sensor or a transducer. This is the very most important element which is kept or placed or connected on our machine. So, this is my machine. There could be a lot of dynamics happening in this machine. It could have having rigid body motions, or the rotations. So, how do we, and then if we have a transducer, the idea is to capture the motion around one of these points. Okay. And essentially this transducer usually gives an analog electrical signal. Okay. Now, this signal which we obtain from the transducer is dependent on the mechanical parameter. So, this electrical signal obtained is proportional to the mechanical parameter which has been measured. Okay. And you all know there is an endless list of mechanical parameters and endless list of sensing element. Rather than sensors, sensing element is very, very important. Same mechanical parameter could be sensed by different sensing elements. For example, either direct or indirect. For example, I have a body which is having a certain motion at one point. Because of the motion, there will be displacement. This displacement could be captured by an LVDT, and that is a linear variable differential transformer, LVDT, or a strain gauge, or a piezoelectric crystal, so these are the different sensing elements which are used to measure the mechanical parameter. Could be mechanical motion. This is just to give you an example of the body. Now, from this sensors I will get an electrical output. Now, you may be wondering yourself, well, why do we have so many different sensing elements? Well, it is because of the fact that these sensing elements have different characteristics. Some may have a poor response, some may have an excellent response, some may not respond at certain ranges, some may not work at high temperatures, some may not have a linear output. So, these are characteristics of sensing elements. So, a transducer or a sensor, a transducer has an essential element which is the sensing element. Sensing element is the most important part of a transducer, and this list of sensing elements is endless in fact. Okay, it is a very large list, but we will try to focus our attention mostly to mechanical motions, vibrations, noise, temperature, process parameters and so on. So, we will home in towards these few mechanical parameters and see, because if you recall, I had told you in the very first few classes that the condition based maintenance around the world, 70% of the cases are by vibration monitoring, rest 20 by wear debris analysis, and the remaining 10 by either by ultrasonics, NDT techniques, motor current signature analysis. So, we will focus our attention to mostly how do we correctly measure vibrations and how do we correctly measure temperature, pressure, current, and the wear debris parameters. So, with that we will be kind of looking into these elements. So, coming back to our discussions on the sensing element, there could be LVDT, strain gauges, piezoelectric crystal, etc. But between the machine I have certain intermediate step wherein I put a transducer. I will have some intermediate unit which is essentially a signal conditioning unit, and then we will have the either the display or the analysis unit, and of course, associated with this there are a lot of secondary devices like a archival device to store the data, to plot the data, etc. We are not going to discuss this. So, depending on this transducer output, my signal conditioning element could be many. I have listed few of them in here in the slide. One is definitely sometimes an amplification is required. I will give you an example of an amplification which is used mostly in condition based maintenance. For example, we are using a thermocouple. Okay. Suppose a thermocouple at a certain voltage, a certain temperature gives only about 3.5 millivolt. Okay. And with the if you recall the measurements done by thermocouple, when the temperature increases, this voltage output will increase, because 3.5 millivolt will never become 10 volts. Okay. But this goes 3.5 to maybe 2 volts and so on. So, the range given by the output produced by the sensing element may be from 0 to 2 volts. Okay, that may be very small compared to the range of display which I could have. Or for example, recall back to the lectures on data acquisition. Okay. Is the minimum voltage the data acquisition unit can sense is say 1.5 millivolt. Okay. Or let me take this, say 5 millivolt, and this is an hardware requirement, a characteristic of the data acquisition unit. Now, if my thermocouple output in this example is 3.5 millivolt, obviously my display or analysis unit, because data acquisition unit is actually sitting in your analysis unit, I am not able to capture or sense the thermocouple output. Now, that is a problem I have. So, obviously, I need to amplify. So, amplification is a solution to the problem. Okay. Maybe I will increase it by a gain of 10, gain usually written by multiplied by 10 x 10 or multiplied by 10. That means, this becomes 35 millivolt. Okay. So, one such intermediate unit or signal conditioning unit is an amplifier or an amplification unit. But this may sound very easy, I have increased the voltage again by 10 volts, but I also am amplifying the noise. Okay, this is an associated problem. So, how do you remove it? So, there are issues. Okay. Once this noise has increased, I could always, for example, to begin with, my signal in the time domain looks something like this. Certain voltage. If I am going to increase it by a factor of 10, maybe this will all okay. This becomes by 10, and this is my original signal. The black one is the original signal. Okay. I have amplified the noise, but then you will see sometimes there are detectors. If I put a detector that you sense only the peaks, I should be able to sense the peaks. This is in time domain, but sometimes here it is in, sometimes we can do certain filtering. Because in the frequency domain, if I know my signal is in this band, I can put a band pass filter. So, it is going to eliminate the noise in the bands which are not of interest. So, this is my F lower and F upper, and this will have a center frequency F C. Depending on, you recall your understanding of filters, whether it is an octave filter, 1/3 octave filter, it is a linear band pass filter, we can decide on this, or whether it is a notch filter. Particularly when we do measurements in mechanical systems, wherein there is an electrical power supply, there is a problem of what is known as an electrical ground loop. Okay, this is very important, particularly in many measurements when we do at site on condition based maintenance. What happens, suppose I have one machine and another machine, okay, and they require an, say, an AC power supply. Okay, they require an AC supply, machine 1, machine 2, right. And suppose physically this is the ground potential of this, ideally it should be 0 voltage, but you would have seen in many cases, suppose this is a 2 volt, instead of a perfect ground is that a 2 volt and this is at 0 volt. So, if I do lot of instrumentations and I conduct each one by wires, okay, there will be a flow of current, because the potential difference is only 2 volts, this is good enough for a current to flow, and this current will flow at the supply frequency of 50 hertz. So, any measurements, if I have put a transducer here, if I put a transducer here T 2, T 1, and then I go to my analysis, common analysis unit, okay, you will see, because of the potential difference, because this has a separate power supply, this has a separate power supply, and one is at a different ground. We may very notionally say, well, they are all at the same ground, but in real life between rooms you would have seen one is not at perfect ground, that is perfect earthing. Even if a 2 volt is there, this is large enough for a current to flow, and whenever we do the analysis, you will see in the frequency domain, you may be doing a vibration measurements, all the vibration measurements will come, but there will be a strong 50 hertz signal. Okay. This is a real problem with instrumentation, and once we go to the field, we have to avoid ground loop. Okay. Well, I will just tell you some of the tricks to avoid ground loop. One is, wherever possible, use DC power supply, battery source. Next is keep all at a common ground. That means, if all the potentials all are common, then this there will be no potential difference and then there will be no flow. Or make sure earthing is proper. Sometimes I have seen earthing voltages of 10 volts in a very poor earth, and this is responsible for, because this signal carrying cables are actually metal conductors. So, there is path for the electrons to flow, and they get buried in the signal which is being captured by the transducer. Okay. So, this could be done by having a proper intermediate element, which is a signal filter. I could, the next one I could have number 4, is a notch filter. That means, from the signal it is going to remove the 50 hertz component. Okay, so, 50 hertz effect will be removed. Few more amplification units are say linearization. Particularly sometimes in some strain gauges, etc., the outputs are not linear. Okay. Suppose my output with time or with certain range is some x and y parameter. This is my output. So, I could, because if you imagine, because if this was my mechanical parameter, and this was the corresponding electrical voltage, you see lot many oscillations. Okay. So, either through a device, either analog or digital, I could linearize the response. While we are doing the measurements, if you have my transducer, the intermediate unit and the display unit, these are all analog signals. So, there are analog linearizers or linearization units. These are my transducers and this is the readout unit. Okay. So, because the signals are analog, we have to have certain sets of electronics to do the linearization. But again, I will just tell you, because we had courses on digital signal processing. Had I given you this red signal on a computer, you could have very easily linearized it, which you all are doing while you plot an Excel graph or do a regression analysis. Okay. So, you can imagine the power of digital signal processing. Think of the days when digital signal processing were not available, where computers were not available. How were people getting linear output out of sensing elements? They had to have some electronic hardwares to do that. Okay, but gone are those days. Nowadays, I will just get the signal from a transducer by having a proper data acquisition, take it in the computer, put a software, do the linear output. Okay. And the next element of this instrumentation, of the last element, very important, is the data presentation element. Okay. Because finally, either you can call it as data presentation or data further analysis, or because once the signal has come from the transducers through the signal conditioning element to the data presentation element, we have to now see the format in which the data has to be presented. Sometimes, once the data presentation is done, we have to do the data analysis. Now, this presentation is in a proper format. This format could be, if you are just doing a measurement and reporting it, it has to be as per the format of the report or a standard. Now, this presentation, whether it is analog display or a digital display, whether this data which has been presented, whether it needs to be archived or stored, it may go to a database, because finally our CBM software or technique will be working from this data only. I can store them if the data is large. Should I store them in ASCII characters or binary, because the storage space is very important. If I am doing all these measurements, imagine you can complicate you have a small laptop, handheld laptop, and you have to do the measurements all around the plant and capture all the data into your laptop. Imagine in one day you are going to fill up your hard disk. Okay. So, the format of storing the data, if there are certain image files, we cannot be storing large image files. So, that is why all these formats of JPEG, TIFF, all those compression formats have come up. You must have heard of zip files, because only the process is to compress the data. So, binary method of storing data is much useful in the sense that the memory requirement will be less when you are storing digital data. Earlier days, if you go to any plant control room, particularly if you go to the plant control room of an electrical power station, you will be noticing that there are a few engineers or operators looking at the wall full of dials. Okay, they have many critical components which they will be recording. In fact, many of the steel plants, cement plants, etc., around the clock when their production, the shift in charge do nothing but they will be maintaining a log. Okay, I mean the next day morning the in charge is going to come take a look at it. But these are done about a decade ago. Nowadays everything is automatically data logged, and if there is an deviation, you will either get an alarm, maybe on your mobile phone. Okay, you are sleeping at your house, you will get a mobile phone, such and such bearing in your plant has become abnormally hot, and this is the state of the art nowadays. I mean earlier days, 30 years ago, 20 years ago, steel plant, what they were doing in the control room in the night, they were just logging down in every half an hour. This is the temperature of that blast furnace, this is of that coolant pump, this is of this gearbox, that gearbox, temperature, pressure, flow rate, all this, and this was being done manually when all the computer aided data acquisition systems were not available. Nowadays, you need not worry, it is totally manpowerless. There is no manning. Okay, everything from all the data transducers are put permanently around the instruments, signal analysis units are there, data is being logged into a computer, and data if the suddenly some data are there which are abnormal, which are not as per the prediction models, you will get enough alarms. Alarms could be right there at the plant, alarms could be right there on your mobile phones also. Okay, and that is what is the present state of the art. Okay. So, well, essentially all this which you have discussed so far are the elements of instrumentation, and to summarize, the three elements of instrumentation are the most important is the sensing element, then is the signal conditioning, the intermediate equipment or analysis unit, and then the data presentation element. Okay. Now, let us see what are the different transducer elements available to us to do measurements. If you look at the two broad classifications, one is the analog transducers and other is the digital transducers. In analog transducers, we have the electromechanical type, basically a resistance type, an inductive type, a capacitive type, or a strain displacement type. Okay. So, this is the technique. I mean, these are not the mechanical parameters. Mechanical parameters could be anything, but by having this sensing elements, I can measure the mechanical component. I will just give an example here. So, for example, all of you know what a strain electrical resistance strain gauge is. It measures strain, but you see this strain gauge could be used to measure a mechanical parameter displacement, another mechanical parameter as a load or a force, which are actually load cells. Okay. suppose I have a member, okay, because of certain force. This member is either going to get an axial pull or compression, and then if I put electrical resistance strain gauges here, because of this load, compressive load, I will get a strain. So, by measuring the strain, knowing the parameters of this member in terms of the cross sectional area, the Young's modulus, the length, I can indirectly measure what the force load is, and that is what is a load cell. So, an electrical resistance strain gauge is this sensing element, but the mechanical parameter could be load, could be displacement, could be pressure. For example, there are diaphragm types of pressure gauges, okay, and these are held in this is a thin membrane. And there is certain pressure here P, and this of course this is there in housing, etc. Because of this, what is going to happen is this membrane is going to have a deflection, right. Now, on this membrane, suppose there are certain strain gauges attached. So, because of the pressure, this membrane is going to deflect. Because of this deflection, the membrane will have a strain, and that is again sensed by the strain gauges. So, strain gauge has become a sensing element. Mechanical parameter could be pressure. Instead of strain gauges, I could have put piezoelectric crystals, they would have produced a charge. Okay. So, some of the, for example, microphones. In a microphone, we have two membranes or two discs rather, and they are maintained at a certain potential. Let me draw it on another page here. It is a very thin membrane, like a metallic foil, okay. And then this is another base plate, metallic. So, if there is a pressure fluctuation, this pressure has become because of the acoustical waves which are being incident. So, what is going to happen? This membrane is going to deflect as per the pressure waves which are incident. Okay. So, what is going to happen? So, this is going to happen, this gap is going to change. Because this gap has changed, its capacitance has changed. So, by sensing the capacitance, change in the capacitance, because the capacitance has changed, the charge produced will be changed, okay, and because they are maintained at a particular voltage. These plates are maintained at a particular voltage. Now, the capacitance has changed because the gap has changed, and then we will get a charge which is corresponding to the mechanical pressure P. So, these are what I mean are the sensing elements: resistance, inductance, capacitance, strain, etc. And these are used as sensing elements in mechanical systems to measure the mechanical parameter. Instead of strain gauges, we are also nowadays using piezoelectric crystals. In fact, in CBM, some of the instruments which we are going to discuss are basically nowadays having piezoelectric crystals as the sensing element. And some of the other type of transducers are the digital transducers. They will generate the frequency generating type or the digital encoder types, wherein we will get a pulse strain, and by measuring the pulse width we will get the frequency estimation. Okay. And these are used in particularly in CNC machines, lathes, etc., to find out the speed fluctuation, etc. Okay. Now, based on these sensing elements, certain transducers are built, manufactured, and then we use them in CBM. But then these sensing elements, so if I was to go back to the discussion of the pressure gauge, so input, so the measurement chain in an electromechanical transducer are these three. One is the physical variable. Physical variable could be the load force in the case of a load cell, pressure in the case of a pressure gauge, but the primary sensor is that mechanical displacement or strain. It was that membrane which deflected, and on that membrane I had kept a strain gauge, I could have kept a piezoelectric crystals. That was my primary sensor, and then I will get an output which corresponds to the characteristic or deflection of this sensing element, strain gauge or piezoelectric crystal, and finally, I will get an output. So, everything put together is an electromechanical transducer. Okay. So, now a transducer is a little bigger superset of the sensing element. Excuse me. Okay. Now, once we have understood what these transducers are, well, let us see how do you know whether we are measuring them correctly. So, some of the static characteristics, because the primary mechanical parameter as a function of time mechanical parameter could be anything. It could be either static, not varying with time, example temperature in this room, almost static, okay, or the parameter is changing with time, maybe the, so this is the dynamic. Examples: vibration of a structure, voice signal in this classroom. Example here in static case is the temperature. So, the mechanical parameter is either a static or a dynamic having a dynamic characteristics. So, that means static means it is not changing with time, it has a DC value, it is not having any frequency, but dynamic means it is varying with time. So, it has a frequency content. Okay. Now, what are the frequency static characteristics of an equipment or a transducer? For example, I know, I will give you an example. I know that this is my actual quantity which is to be measured, okay. But each time I measure, I am reporting these values. Okay, this is one case. Another case could have been this is my target of the bullseye. Another is okay. These are the cases. Another could be I am all over the place. Okay. And another could be I am okay. So, I will just, this is my target. this case I am precise in the sense that I am always measuring around a particular value here. Here I am accurate, but not quite. In this case, I am both accurate and precise, and this I am neither accurate or precise. Okay. The best would be this kind of instrument, wherein I always measure accurately and precisely. In the first scenario, there is an error, there is an actual offset. Okay. So, this offset, if I know this value, I can always remove this offset and get the correct measurement. So, this is the measurement has been biased, a constant shift. So, this is the case of a bias error. Okay. And here in the case of accurate, if I did more averages, more measurements and did many averages, I could be perhaps close to the target. So, this is the case of an random error. Here I have both random and bias errors, and here I have removed both the random error and bias error. So, you get a feel that in any measurement this happens, but my CBM wants only this, we have to be both accurate and precise. Okay. So, today if you go to the market to buy a thermometer, you will get a thermometer for 5 rupees, you will get a thermometer for 20 rupees, you will get a thermometer for 2000 rupees. Okay. Not that the cost is towards the profit margin of the supplier, but it is for these values. The same amplifier, same vibration meter which we use for accurate scientific measurements and R&D are very costly. Same microphones which I am using here could be 100 rupees, but then there are microphones which are 100,000 rupees doing the same thing, but they are more accurate and precise because of this scenario. So, accuracy and precision go hand in hand, and then as CBM we have to remove this bias error and random error, and this is done by random error reduced by doing more averages, bias error by doing a calibration. Okay. And some of the important other characteristics are the resolution, sensitivity, range, hysteresis, impedance, etc. Resolution is the least value which my measurement system can measure, and so on. And so, in a static instrument which we use for measurements, we have to be very careful about whether it is accurate, whether it is an accurate instrument, whether it is a precise instrument or transducer, and you will see because how accuracy and precision can hamper your results. And now, let us come back to the dynamic characteristic of an equipment. Okay. By the dynamic characteristic of an equipment, I mean, or a transducer, that means if my mechanical parameter which is to be measured is varying at a certain rate, it is varying at a certain frequency, is not it? Now, imagine that means high frequency means it is varying at a high rate. So, my measurement system cannot be slower than the mechanical system, is not it? Suppose every instance the vibration is changing. I cannot come with a transducer which will measure vibrations only at intervals of 10 minutes. So, I am going to lose this phenomena, is not it? So, my instrument has to react faster than the quantity or the mechanical parameter which I am measuring. That is very, very important. I use the word react quicker, because of the fact every mechanical transducer has inertia, has stiffness, has a natural frequency, and if you recall, this natural frequency is nothing but stiffness by mass. If mass is low, then natural frequency is low. Okay. So, if I want a very sensitive equipment in terms of very fast response, its mass has to be less. I will give you another related example. You know, many of you must have seen the jockeys riding the horses on the horse track. Okay. Have you seen why the jockeys are very less weight, the person who is riding the horses? Because my objective there, the horse has to go from the starting point to the finishing point quickly, and jockey is loading the horse. Okay. The horse should not become sluggish or should not react late, because it has got loaded. Okay. So, that is why jockeys have of lesser weight. Same token here, if my mass is very heavy, the transducers will be having a very, very poor frequency response. They cannot react faster. Okay. You would have we all cut jokes with persons who are overweight. They do not have, they have a poor reaction time because of this. Similarly, transducers which are heavy and bulky, they cannot respond fast to the mechanical parameters which are sensing. Okay. So, we have to have sensing elements which will react faster or which will have a response quicker to them. So, now going back to the transducers, because the transducers, because they have natural frequencies, if I was to plot the natural frequency response of a transducer, maybe certain parameters. So, this is the natural frequency of the transducer. So, I should be doing my measurements in the band much away from the frequency response of the frequency natural frequency of the transducer. So, this is my useful range. Okay. So, if I was to define the frequency response of an instrument, that is the response of the output to the input in the frequency domain, usually given in decibel. Because if my input is having a certain characteristic, the output should be identical. So, this in the decibel scale will become 0 decibel. Because if I come to these ranges, my output is getting affected by the natural frequency of the transducer, because we have to live with it. The transducer has a natural frequency. So, my output cannot be getting amplified, because I am measuring in this frequency range. So, every transducer has a useful frequency range, wherein the output to input ratio is 1, or in log scale this becomes 0 decibels. Okay. Similarly, we have the time constants. So, here I will direct you to my website www.iitnoise.com. In this website, if you go to the student resources page, there is a tab on virtual labs. So, if you go to the experiment number 2 in this virtual labs, that is the response of mechanical systems, you can have an understanding of the response of first order, second order systems. So, you all can go to this place and just for your self study look into this website. Okay. So, well, you must be wondering why do you always use electrical signals? Because of these inertia and friction effects are absent, amplification can be obtained with relative ease, and recording from a remote distance is also possible, because electrical signals I can transfer it to large distances, which is not possible by mechanical systems. I cannot have linkages and relays and bars for large distances, and that is why in a transducer traditionally we have been using all the sensing elements and we get an electrical output. And then we just had discussed about this measurement errors, one of the bias error and the random error, and of course, they can be removed by having proper calibrations. So, calibrations and measurements, of course, measurements have to be done as per the international standards, because once we report our vibration measurements done in lab A to lab B, we should ensure that the same standards or equipments were calibrated, so that the data is reproducible and data can be exchanged between different communities and groups. So, when we have the frequency response of the transducer and in an entire measurement chain, when you are talking about a transducer having a good frequency response of 10 kilohertz, and I put a signal conditioning unit of a response up till 5 kilohertz and digital display of only 2 kilohertz, I cannot say that I have a 10 kilohertz bandwidth of measurement, and that is the important mistake people do, and we will discuss that in the subsequent classes when we talk about the transducers. So, we have to keep in mind that the frequency range and the dynamic range of the measurement chain, and dynamic range is nothing but the ratio of the highest to the lowest values, which the same sensing element can sense. Okay. We will now, with this kind of background, with this instrumentation, we will now be specific, we will discuss about the specific transducers in the subsequent classes. And in particular, some of these are the transducers which we will be discussing, because these are the mechanical parameters: vibration, noise, rotational speed, current, temperature, flow rate and thickness, and these are the transducers which are conventionally used, like accelerometers, microphones, key phasers, phototach, RTDs, flow meters, ultrasonic thickness gauge, and these, the principles behind this equipment we will be discussing in the subsequent classes. Thank you.